Hello, I'm Jay Sanguinetti. I'm the Assistant Director for the Center for Consciousness Studies. Just got off an airplane from Ibiza, which is a pretty fun place to go. I had no idea there were so many parties in Ibiza. So I'm really happy to introduce the last workshop for today. This is brain-computer interfacing, and with some neurotech on top of it. We've got a lineup of about 7 speakers, or exactly 7 speakers, actually. Each of them will do 15-minute talks on either BCI, neurotech, or the combination. These are technologies that will influence consciousness, help us study it, help us lead to better products of well-being, and ultimately how we use that technology to close the loop for closed-loop stimulation. We will have 15 minutes for each talk, and then we'll go into a panel for Q&A, so you guys can ask questions, and folks online will be able to ask questions as well. And I'm very happy that Anna will give us a nice welcoming Barcelona style.
Thank you, Jay.
Yes, thank you.
So, hola a todos. Buenas tardes. Welcome, everyone. I know many people in the room, and as you know, Neuroelectrics is a Barcelona-born company, but Boston scale-up, so I have spent a lot of my life in Boston. And I'm so happy that once you're coming to Barcelona, so welcome. And I just wanted to give you a few tips. I mean, Barcelona is an amazing city. I hope you have the chance to go around town. Enjoy the Dalí architecture, the Gaudí, all the buildings. Go to Sagrada Familia if you get tickets, to La Pedrera, get a swim in the beach. And it's not only that we have the best food and the best architecture and the best entrepreneurial culture, but it's also a vivid ecosystem of technology and startups. And I'm also proud that in the neuroscience space, we follow the steps of Ramon y Cajal, which is a Nobel Prize laureate from Spain. So I think it all comes together. And if you are in the Tibidabo mountain, even if you stay for a few days, you can come to our offices, which is at the top of the mountain, and then we can let you try our now famous EEG and neuromodulation brain stimulation device. So many people will recognize me now in the room. But I just wanted to really, really welcome you to Barcelona, and I hope that it's not all work, but you have the chance to talk to the people of the city, enjoy the food, and the wonderful architecture and culture. So bienvenidos, and I hope you really solve the quest of consciousness, which is a simple one. So good luck. The talks first, okay.
Is that open?
All right, so there we go, audio. Fantastic to be here with you all. My name's Tim Mullen, so I'm just going to set the stage a little bit for the next session here around brain-computer interface technology. This is a video showing a real-time fly-through of brain activity, brain connectivity, and underneath that, decoders that are translating the activity of the brain into actions that can be used to control devices out in the world, or can be used to sense your state. This is a brain-computer interface. And brain-computer interfaces sit at the convergence of 2 fields, neurotechnology and computing and artificial intelligence. This convergence has been happening for quite a long time, actually, but we're now entering into the hyper-accelerated phase of this field, primarily because of the growth of AI and the growth of material science and technology for neurotech. What is a brain-computer interface? We define it as a system that measures brain activity and then converts that brain activity into functionally useful outputs. And those are outputs that can be used to replace, restore, enhance. So over here, replace, restore, enhance, supplement, or improve the natural outputs of the brain. And research can also be a part of that as well. And this can also include things that modify brain activity through different kinds of stimuli. That can be sensory inputs, or that can be things like brain stimulation. A brain-neural computer interface, the BNCI, is defined as something that extends not just signals from the CNS, but also the peripheral nervous system. So eye movement, heart, things that measure your cranial nerves, things like this. And there's a bunch of other terms that have been used here. These are all kind of synonymous. Like a brain-machine interface means the same thing, a neuroprosthetic, direct neural interface, they kind of all mean the same thing. So these are the classic definitions. Now, a lot of what we're going to talk about over this talk and also in the coming talks can be broadly defined as neurotechnology. So if we kind of zoom out, we can say neurotechnology is any technology with the capacity to measure and analyze chemical or electrical signals, also other types of signals from the nervous system, and then to interact with the nervous system to change its activity. So what are the current and emerging applications of neurotech? There's quite a few of them. Assistive technologies, this is where brain-computer interfaces traditionally have been used as a subset of neurotechnology. That includes things like this, which is called an SSVEP, or Steady-State Visual Evoked Potential Speller, where a person's able to write about 1 character per second, spell out words, sentences, by BCI that is measuring this person's attention, what they're paying attention to on this display. Here's a video showing Kathy Hutchinson controlling a robotic arm. She's using the BrainGate implant to control a robotic arm to take her first sips of coffee unaided. Over here, you see human and AI interaction and augmented cognition. This is a more recent application of brain-computer interfaces. Perhaps in the last 15 years, this has become more of a sector. This is an example of this, where here I'm actually sitting in this plane measuring brain activity from a pilot who's flying a plane, and what we're decoding is whether the pilot was unaware of a warning sound that was played in the plane. This is called inattentional deafness. And this is now informing then the system that this pilot did not hear the sound that was intended to be played, thereby providing additional information to the environment. That's called a passive brain-computer interface. So this is areas where AI systems can be knowledgeable about our internal states and then aid or assist us in useful ways and maybe augment our cognition. Over on the right here, we have quantified self, health, and wellness. These are devices that read our mood, read our sleep state, and help to generally provide us information about ourselves that we might otherwise not have direct access to, unless you meditate frequently, and then you'll have all this anyway. Down on the bottom here is closed-loop neuromodulation and neurotherapeutics. This is an example of somebody using a closed-loop neurofeedback system. It's tracking default mode network activity. This is one of the networks that's modulated when you meditate. So as the person changes the activity in that network, it can levitate these orbs, giving the person feedback into their own internal brain state, helping them then access those internal states more easily, perhaps get into the meditative state a little bit more easily. Neurotherapeutics also is a field where we're doing things like direct brain stimulation to treat the brain. This is an example of transcranial focused ultrasound. This actually, I think, is Jay's head in our office at Intheon years ago. And pulses of ultrasound stimulation are being used to change brain network activity. And you can see in real time the tracking of those responses of the brain, the network responses and the source activity of the brain. So increasingly, these are becoming part of brain-computer interface technology as well. So both neuromodulation and neurotherapeutics are often used in a clinical context, but increasingly are to sort of change and improve the state of a person's brain, even things that allow to treat different things like depression or anxiety. But increasingly, they're being used also in consumer areas. And neurofeedback's been used for a long time in the consumer sector. Finally, there's entertainment and experiences and art. So this is actually some of the first applications of brain-computer interface technology. But these are examples where you can decode brain activity and use that to control things like lights, sound, music that's based on your internal state. This is Mickey Hart, drummer from the Grateful Dead. I'm sitting next to him with a VR system. We're flying through his brain in virtual reality, and we're measuring and tracking a whole bunch of different things about his brain activity while he's drumming, and then we can present that to the audience. We can provide feedback to Mickey in his own VR world about his own internal state as well while that's happening. Yeah, and so Mickey's great. And there's a big drum circle, 700-person Grateful Dead type Dead Fest with weird tech. This was fun. So those are some of the applications. What are the different categorizations of current and emerging neurotech? Well, here are some of the different technologies for reading from and writing to the brain. This is from a paper that Eric Leudhart and I wrote with Dan Moran. And what we see is that as we go from technologies that are outside of the brain to technologies that are inside the brain, we get better precision at listening to the neurons inside the brain. But it's also, there's a higher risk. We're putting electrodes inside of your brain. On the outside of the brain, we've got things like EEG, electroencephalography, near-infrared that measures scattered light from the brain and can tell us about oxygenated blood flow, things like transcranial focused ultrasound that can stimulate the brain and also can potentially read activity as well. And then as we move into the brain, we have a whole bunch of different types of interfaces. The least invasive are things like intracalvarial interfaces. These go in the bone. There's a company I co-founded called Intercosmos that develops these to treat depression, stimulates and reads from the brain, but inside the bone. You have intravascular interfaces. Those go inside your veins, and they snake up into any area of the brain a vein can go, and they can record and write to the brain through those interfaces. And then all the way down to neural dust, which are small little motes that can be implanted and wirelessly powered. We'll talk about that in a second. There's also a lot of different ways that non-invasive technology in general can be worn or can be used. So they can be worn on your head, they can be worn in eyewear or in VR systems or head-mounted displays. They can be worn in little hearables that are inside of your ear. They can be worn in your clothing. These all are possible ways to record the brain activity. Even little tattooable electronics on your skin. Some of the input methods, the ways of changing the function of the brain, include, we already mentioned things like transcranial focused ultrasound, but there's also current you can use, electricity. You can use magnetic fields to change the activity of the brain. You can use photobiomodulation. I believe Lou Lim will talk about that, light. And you can stimulate also the peripheral nervous system, like the vagal nerve or cranial nerves, to change the function of the brain as well. So there's a lot of different ways we can put information in, and there are a number of different ways that we get information out. These are some of the EEG types of systems that are currently being used for BCIs. On the left, we have high-density systems with up to 256 electrodes. And on the right, we have one-channel or two-channel systems that can be worn anytime, anywhere. As you go to lower dimensional systems with fewer electrodes, you do lose some information. So it's a trade-off between how wearable a thing is and how much information you want to be able to extract from the system. So I want to give you a quick, very brief tour of just the history of this field to set the stage for the other speakers. So we'll just blast through this in like 3 minutes. Basically, this all began back in 1924 when Hans Berger discovered EEG. And he was actually looking for evidence of extrasensory perception that he believed he and his sister shared. They had some profound experiences that made him convinced that there must be a way in which brains communicate to each other. And so he went to search for that, and what he found was that the electrical signals emanating from the brain that seemed to correlate with brain states. This led to the inquiry into what this was, termed the electroencephalogram, and from there we got EEG. EEG, these signals correlate with the internal states of the brain, but it wasn't until Norbert Wiener came on the scene and defined cybernetics as a method of control and communication in animal and man that people started asking the question, can these kinds of signals be used for communication, maybe? So José Delgado in the 1950s, he was the first person to develop and demonstrate, large scale publicly, the ability to change and change the function of an animal or a human by stimulating different areas of the brain. And here he is with a bull charging at him, and he presses a button and wirelessly transmits a pulse to an electrode implanted in that bull's brain, and it stops the bull. So this was a very sensational experiment, of course, putting his life on the line. But he was demonstrating there the ability to, enact control, basically, through these systems. Obviously, that raised a lot of ethical concerns even back in the 1950s, and the same concerns exist today. What will BCIs be used for? Early BCIs were used in the arts in the late 1960s, or mid to late 1960s. And here, this is Alvin Lucier, who's creating music based on his alpha waves. Then BCI finally was formally defined by Jacques Vidal under the ARPA program in 1973. This was his room-sized computer that now can go in a little chip this small, but back then it took a whole room for decoding brain activity. And then in the 80s, we got the first things that were practically usable for communication, like BCI spelling devices, like the one I showed you earlier, where people could type things just by thinking. That enabled locked-in patients to be able to communicate. That was using the P300 electric wave. We got the first human with a brain implant for prosthetic control in 1998. This was Phil Kennedy's neurotrophic electrodes. And then BrainGate was the first really widely demonstrated computer cursor control capability that came in 2004. This is Matthew Nagel, who was the first person implanted with that. Optogenetics is a method that came right after there. It allows us to write and control neurons with light. Very powerful method, but you got to hack your genes, so people aren't doing that today. And then finally, in the sort of mid-2000s, we got consumer BCIs and wearable EEG. Here we have Anna with her famous cap, leader in the consumer BCI space. We also have Ariel Garten from Interaxon or Muse, Tan Lei. So we got on the scene all of these devices that now made it possible for us to record brain activity anytime, anywhere. And that really actually created the first wave of public interest into BCIs. Epidermal electronics, tattooable electronics came online in 2011. The first brain-to-brain interface in 2012, transferring sensory motor information from one rodent to another, Miguel Nicolelis. And then we started getting a whole bunch of advances in things like the neural dust motes that go inside your brain, the stentrodes that go through your veins. This was a little side thing. We did the world's largest collaborative BCI, 700 brains linked up over the internet in 2017. And finally, in 2016 to 19, big tech started getting into BCIs. Facebook or Meta, Neuralink, Kernel, you saw a lot of press around BCIs. And that's where it became the kind of thing your mom's like, oh, you're working with Musk on something. At that time, Elon was the only person that was known to be doing BCIs, it seemed. But yes, that was when it became mainstream. And now over the last 5 years, we've had a lot of advances through deep learning and generative AI that are really accelerating our ability to decode and build closed-loop systems that can both measure and also write to the brain in real time. So what's happening in the future? There's a lot of new advances that will be happening over the next decade. A lot of it will center around new types of technologies that are less invasive, more easily used, wireless and cloud connected, the ability to make better robotic systems coupled with brain activity to help people who have injuries to be able to feel again, to be able to see again and sense with all of their full sensory apparatus. And then finally, the merging of BCI and AI with biocomputing and things like this are going to lead to some unforeseen, we don't know what it will look like, but it's going to lead to new types of BCIs that are merging both AI systems and BCI systems. What I'm most excited about is BCIs for mental health. How do we use this to help improve well-being and flourishing? How do we use BCIs to help people to regulate their own system better? And finally, what we might call neurodelics or neuronosis or spirit tech, the ability to use these technologies to help people to have deeper and more profound experiences of source, of the things that make it worth living and finding purpose. We don't need the technology for that, but it could help people to be able to access some of these states, as psychedelics have done, as meditation has done. Mark Weiser said the most profound technologies are those that disappear, that weave themselves into the fabric of everyday life until they're indistinguishable from it. And he also said that the more you can do by intuition, the smarter you are. The computer should extend the unconscious. Technology should create calm. So he was the person who led Xerox PARC, which created everything that we use in our computing systems today, for the most part, including the operating systems, the mouse, the TCP/IP, all of these fundamental frameworks. But what Mark Weiser really saw was that the purpose of technology was to disappear and not to be the dominant thing that controls our attention in our lives, and to help create calm. This is a quick example from a TEDx talk that I gave. That's my wife on stage. There's no audio, but if there was, is there audio? It's okay if there's not. She's saying, she's saying Neuroscale, or Alexa, ask Neuroscale, which is our cloud platform for decoding brain states, ask Neuroscale for my relaxation level. And then Alexa is saying, oh, your relaxation level is like 38%. Maybe you should try taking a break or meditate. And what's happening is in her ear, she's wearing a brain sensor that's recording her brain activity and her heart activity and sending it to the cloud. And there's all these different measures of her relaxation state, et cetera, being decoded and sent through the Neuroscale platform to Alexa. So now she could be walking around anywhere and just ask the system or the environment, hey, how am I doing right now? And it's like, okay, take a little break now. So we can have these types of technologies just vanish, where they're not the thing that are dominant in our lives, but are in the background of our daily life. I'm going to leave one quick note here on just ethics, stewardship, and sovereignty. So the technologies that are being built are powerful. They have a profound ability to change the way that humans act and behave over the coming decades. So we need to treat them with great care. We have to design with care. And there are three things that I think a lot about. Stewardship. We're not owners of any of this technology. We're stewards of it for future generations. So we have to think about that when we're building this stuff. Does this serve our future descendants and the planet? Sovereignty, human agency, and autonomy are inviolable rights. So any technology that compromises those things should not be developed, period. So we have to think a lot about that. Ethics, we need to build the ethics into the foundation of the technologies that we design and develop so that they serve people, planet, profit, and purpose, a quadruple bottom line. And there are models that solve this. They're called for-benefit economic models. They're very compelling, and they ultimately allow us to target flourishing as our main design criteria, being able to provide relief from suffering, fulfillment, insight, skillfulness, and service, and a balance of these that allows us to live healthy lives. Neurotech can actually address all of these to some capacity. It's not going to replace other amazing tools, meditation, compassion training, having good friends and family, and just a wholesome life. But this is the core of where we want to be at the end, leaving the world a little better than we found it. So thank you, and if you want to learn more, reach out.
Very nice. All right, thanks so much, Tim. And obviously, you guys you heard from one of the world's experts in BCI. Go ahead. You are about to hear from another expert, Arnaud Delorme. Arnaud is the creator of EEG Lab, which I've probably spent more of my graduate school career in than anything else I did. This is the EEG software that a lot of people use to process EEG. Arnaud has also done, I could sit here for hours talking about all the cool stuff he's done, but a lot of things in BCI as well as in the meditation and wellness space. I think today he's going to talk about closed loop BCI and maybe a little bit about mind wandering too.
Yes.
Cool.
Thanks, Jay. Yep. 1, 2. So first, I want to give a little background, where I'm coming from. And I remember when I was 12 years old, I was in the suburb of Paris at my school. In the courtyard, I thought I wanted to be a firefighter, but I got this insight, no, I want to understand why I'm here. And in my upbringing, Western science, that meant, well, if you want to understand why you're here, you need to become a neuroscientist and you need to study the brain. So that's what I did, and then I realized, well, I also need to study myself, did a lot of meditation retreats, and I realized my mind is wandering all the time. And for me, that seemed like something very interesting about the functioning of the mind, the mind wandering aspect. So we did first this study with my PhD student, Tracy Brandmeier, and we went to India. There was an ashram in India. They bought this very expensive equipment, and they didn't know what to do with it. So we set up this study in which we enrolled expert meditators and novice meditators. So this is the paper we published. And basically, the study goes like this. So we just ask people, you meditate, you just do your thing. And we're going to ask you a question. It's not us asking question, it's the computer asking question. Every 2 minutes or so, it happens randomly, and it asks 3 questions. Please rate the depth of your meditation. Please rate the depth of your mind wandering, and please indicate if you're tired or not. So this is how it goes. So here is one question. The first question, they might answer, okay, here I was deep in my meditation. Second question, they might answer, oh, now I'm mind wandering. Same for the third question. And then the last one, they're mind wandering. And in these periods right here, That's before the question even happens. So from the perspective of the subject, they're just meditating and we're interrupting them. They don't even know we're going to ask the question. So this is a purely introspective task from our perspective. And so we are comparing basically these periods of meditation versus the periods of mind wandering using brainwave analysis, all the tools that Tim already described. Here we had a 64-channel system. And what we found is that in expert meditators, we found this increase in mostly frontal midline theta, so mostly in these regions, in the frontal regions, when people were meditating. And we also found that expert meditators were spending more time meditating than novices. Meditation does, in this specific experiments, potentially decrease the frequency of occurrence of mind wandering. Okay, so now we know what's the one neurocorrelate of mind wandering, but we also know that in the Western world, people are busy. We don't have time to meditate. We need a machine. We need neurofeedback. So we set up a system where people, and that's a caricature, where people wouldn't have to meditate. They would just train with a computer to reproduce the same brain waves as the expert meditators. So that's the paper we published, and this is the methodology. So what we had is that we have the subject right here, and he's looking at a square. And so here's the subject doing the task, and you see the square is changing. The color of the square is changing, and it's modulated by its brainwave in the frontal midline theta. So that's the same brainwave we found in the expert meditators. Also, we asked the subject to use a meditation technique to try to modulate the color of the square. So here is a more schematic representation where we record the activity of the brain of the subjects. Then we compute the spectral power. Here, I believe it's in FZ. And then we look whether it's above or below a threshold, and we change the color accordingly. So here it's below, so it's going to be dark blue. A little bit later, it might be above the thresholds, and so it will change the color to a lighter blue. Now I want to emphasize some very important points about neurofeedback. Most of you have heard about neurofeedback, but really the devil is in the detail for neurofeedback. So there's two approaches for neurofeedback. There's the Z-score compared to your normative database, and there is the adaptive baseline. So I'm just going to unpack this. So the Z-score compared to your normative database, this is the standard neurofeedback you have in software like NeuroGuide, where you have a population of subjects, usually, unfortunately, not that many, 600 or so in NeuroGuide. And then what you do is that this is a patient, and you try to bring it back to the population average, whether they're below or above in some brainwave frequency bands. The issue is that this is the power spectrum of 15 people, 15 random subjects. And you see the difference here in amplitude is about 15 dB. This means that one person brainwave amplitude is about 6 times lower than another person's amplitude. And there's no way you can push that subject up there to have the same brainwave as the one on the bottom. And so that's why I like to represent here. So you have different subjects, and they have a range they can achieve. So it doesn't make much sense to pull them together into a simple big distribution and call that a normative database. So that's why I believe the standard normative database doesn't work, even though that's the main technique that's used in neurofeedback. This is a little modulated. When you use ratio of frequency, you can counterbalance that a little bit, but still a big problem. So what we use is we use an adaptive baseline. So an adaptive baseline, here's our signal. Here's the upper limit of the signal, and here's the lower limit of the signal. And then what we do is that we rescale that value between 0 and 1, and that's our feedback. So if you keep a constant baseline, what happens is that, let's say the brainwave of the person increased over time. Well, this is going to saturate the feedback and that is not a good experience. So what we did in that specific experiment is that we have an adaptive baseline in which we change the limits over time using a special formula. So the feedback here is still mostly positive feedback. You see it's above 0.5. Is more dynamic, and what I want to emphasize here is that the choice of these numbers is critical. How fast you're going to change this baseline is completely going to change the person experience. And I hope there's going to be more research on that, because just people handpick some values and say, okay, this is what I did. But if you change this too fast, then the person just gets random feedback. If you change it too slow, then you saturate the feedback. So coming back to our study, we had, before the test, we have attentional test using 64 channels. Then we had neurofeedback using 8 channels. And then, again, attentional test. We also had MRI pre and post to check for any change in structure. So this is the 2 groups. So we had 2 groups of 12. We have people who got the actual neurofeedback. They were actually controlling their brainwaves. And then we had sham participants. We didn't get real neurofeedback, but thought they did. So basically, it was the brainwave of someone else that was controlling the color. But they thought they were actually controlling the color. And when we actually asked people, did you think you were controlling the color? All the subjects thought they did. But we can see that the actual neurofeedback group is able to upregulate their brainwave, while the other group is not. Then we had all these tasks, testing, for example, did they decrease mind wandering? Did the task, neurofeedback task, help decrease mind wandering? And the short answer is, in our experiments, it didn't. But we had 3 cognitive tasks, and we had one that was linked to memory. And this is what's called a 2-back task, where you have to remember previous letters. And what we observed is that the neurofeedback group did significantly better than the sham group. So our interpretation that the neurofeedback training here helped at resolving cognitive conflict. So to wrap this up, I also want to mention where I believe the neurofeedback field should go. One of the issues with EEG is the strong correlation of electrodes. So if you have one electrode on one side of the head and another electrode on the other side of the head, they are probably correlated between 60 and 80%. So 60 to 80% is the same signal. And this is because of what we call volume conduction. So if you have one source here, it's going to project to most of the electrodes, even electrodes which are very far away. And same for this other source. So you have 2 ways of solving that. One is distributed source modeling, like Loretta of beamforming, but they have problems on their own because they're very sensitive to noise, especially for real-time data. And the approach I'm using is local Laplacian, which is a very simple formula where you take one electrode and you're interested in the cortical area underneath this electrode, so you take this electrode minus its neighbor. And what it does is that it's computing current density, local current density, and it's much more specific spatially. So you're not capturing activity from all over the brain. If you're more interested in neurofeedback and mind wandering, here's a plug for my book, Why Our Mind Wander, where it explains about neurofeedback, but also meditation practice to tame your thoughts. You can't suppress your mind wandering, but you can try to tame it. And I want to finish on this quote from Rupert Spira. Thoughts are just birds, like birds flying across the sky of awareness. They appear and disappear in the boundless space of our being. Thank you. Do you have time for questions at the end?
We have about 5.
Okay.
I'm going to take a few.
Any question?
Could the air conditioner be turned on stronger?
Okay.
Yeah, it's been very hot. I'm from Arizona. So. Save them for later. We'll have a panel after this as well.
Okay, thank you.
All right, thank you, Arnaud. Okay, next is Giulio Ruffini, also one of the founders of Neuroelectrics with Anna, and one of the world's experts in both reading and writing from the brain, and getting this technology out into the clinic and into consumers' hands. Thank you, Giulio.
Hello, hello. Can you hear me now? Yeah. Okay, thank you. Thanks for the kind invitation to be here. It's a pleasure. Hello, everyone. So I'm going to be talking about probing consciousness in the electrical brain, as you will see. After the previous talk, I don't need to say very much other than that the brain appears to compute electrically. And one question that arises naturally for a physicist, especially like me, is what do electric field patterns have to do with mind? And can we somehow harness them for communication or therapy? So here are three techniques, MEG, magnetoencephalography or EEG, and transcranial electrical stimulation that really interact with the electrical brain. They both rely on the fact that we have these kind of elongated pyramidal cells in the cortex, nicely aligned, that act as a kind of a phase array and that can detect very minute electric fields and amplify them, and at the same time generate electric fields that we can read off with EEG or MEG. You can see on the bottom right a drawing in which I tried to show from a study that we did that actually the electric fields that we generate with TES, with transcranial electrical stimulation, are quite similar to the ones that the brain itself generates, which it's a very interesting point for research. A word about technologies that I will be talking about. TS is transcranial electrical stimulation. It's a weak neuromodulatory technique that does not induce action potentials in the brain. You can see on the top row. And you can see also the value of the electric field it generates, about 1/4 of a volt per meter on the surface of the cortex. And on the bottom, you can see TMS, which is a supra-threshold technique that actually initiates action potentials. And you can see that the magnitudes are very strong, although it's pulse rather than continuous. Applications in BCI, CBI, we have heard quite a bit in the previous talk by Tim. Just want to highlight something that we did some years ago, which is this brain-to-brain communication experiment combining these technologies. So on the one hand, we use a BCI with EEG to read off motor potentials. And this was done in India because at the time, one of the colleagues that was doing the experiment was there. And in France, we actually use a TMS robot to elicit phosphines in the receiver. And in this way, we were able to manage to send communication directly from brain to brain in this non-invasive way. Some other work in which I've been involved with, which is kind of interesting too, it's this kind of matrix type of work, this time with rabbit in the rabbit experiments, in which rabbits were actually trained in a conditioning paradigm to feel whisker stimulation induced by TACS. So a TACS pulse was used to actually have the rabbit feel as if their whisker was being stimulated. And this was shown to be conditioning because then a real whisker stimulation would actually induce the same response of basically closing their eyes. In another example of how these techniques can be used for interacting with consciousness is in this induction of self-awareness in dreams for lucid dreaming. This was work by Michael Nish's team some years ago, in which they used gamma stimulation, 40 Hertz stimulation, and show that this could induce in the subjects lucid dreaming if applied during REM. I won't talk too much about this. You have heard from Tim about certainly invasive technologies now with AI that are being used to actually translate thought into speech, for example, in real time. EEG, there's work in EEG as well with non-invasive techniques, but it's going slower, I think, because EEG is quite a challenging signal to work with, but let's see how that goes, this interesting combination of AI and EEG. Also, some reference was made about TES and EEG as affective interfaces. So in one example, you can use EEG for art generation. You can use TDCS to alter mood. So in this sense, it's also an affective interface. And this is work that we have been doing in both areas. I wanted to show you just
represent the individual's EEG, and it helps scientists and doctors gain a deeper understanding of the intricate patterns.
This is an
within the
example
brain.
of another affective
The
interface.
Experience Lab transforms EEG into emotional data. Emotions are classified in 2D space as valence and arousal. Arousal refers to the general level of alertness and wakefulness of a person, whereas valence is defined in the pleasure-displeasure continuum with values from 1 to -1. The valence-arousal pair is mapped into an emotion tag using the emo-emotion circumplex. NAKD, emotionally, electronically naked, is a pioneering proof-of-concept AI-driven affective brain-computer interface. Brainwave data is collected through wireless EEG and converted into emotional state.
Okay, so this is an example of an affective interface that we actually developed and we displayed in the Sonar Electronic Concert series here in Barcelona, which people loved. Then in another project some years ago, we engaged more directly with this idea of interacting with the brain electrically to alter and measure consciousness, and we explored different techniques, including transcranial electrical stimulation, TMS, EEG. I just want to give you a very brief overview. For example, the perturbational complexity index is something that has been developed basically with TMS combined with EEG. You zap the brain, you observe how brain waves propagate after that initial input, and then you look at the complexity of signals to classify brain state. And this can be applied for disorders of consciousness, for example. Similarly, we explore the complexity of MEG signals. And this is a magnetoencephalography in the fetus and in neonates in this project. And again, using complexity techniques or oddball paradigms, it was shown that you can actually estimate something about the conscious state of the fetus or of neonates the first time. So it's another interesting technique. This kind of techniques use the apparent complexity perspective, which basically is a way of thinking about the brain as a computer is generating patterns, and depending on what these patterns are, you can try to infer what is the state of the brain. So, for example, here I give examples. This is an analogy with cellular automata, in which you have on the left a very simple signal, which is a repetitive signal, which can be if you try to compress it, you will find it's easy to compress, and this could be reflective of epilepsy or deep sleep or disorders of consciousness. On the far right, you have a chaotic signal, which is harder to compress, and in the analogy, would correspond to psychedelics, and in the middle, you have the right balance between complexity and simplicity, which would correspond to a Turing-complete machine in a cellular automaton. There are other dimensions that you can look based on EEG or other techniques, such as complexity, network integration, and segregation. You can look at the networks that the brain forms while it's doing its business and try to infer, based on network features, if the brain is in a given conscious state. And this has been used, for example, again, in disorders of consciousness or others. You can also look at the problem from the neurocomputational circuitry aspect. So you can think about the brain as a predictive system, following the tenets of predictive processing theory. And you can start asking about mechanisms, circuits involved, and hypothesize what states and what circuits are important for consciousness. And you can probe this with different techniques as well, including EEG. Criticality is another view of the same problem of looking at the brain as a computational system, in which one of the tenets is that being near criticality is important for computation, for information propagation and processing. And this can also be used, again, in different brain states, including anesthesia, or, for example, in work I did with LSD, showing that you can use IC models to model what's happening in the brain under LSD and estimating a temperature which is higher in those states, as I mentioned before, with regards to complexity. The challenge in all this, and this is what my talk is really about, is that we are missing a principal unifying framework to define and operationalize what we want to measure. what consciousness is, how to measure it, and understand what its physiological signatures are. So this is what I will try to explain now. In an approach that I've been developing over the years, and now with some collaborators, called the cosmography theory of consciousness, it holds two tenets. The first one is that there is experience. So it starts from the point of view that there is experience. There is an experience field. You can think of it as a quantum field or something like this, that corresponds to the immediate subjective sense of what it feels like to be yourself. And I think people in the audience here know what I'm talking about. Sometimes it's a bit harder to explain this outside. And the theory proposes instead to focus on what structure experience is and what gives rise to this structure. So by structure experience, I mean the spatial, temporal, and conceptual organization of first-person experience, 5 minutes, of the world and of ourselves as agents in it. The idea behind this is that our brains build models to track the world, and for doing that, they need to coarse grain and compress and extract the structure, some structure that can be used for survival. And what is special about the brains is that two things. One of them, that they can compute, as I mentioned before. This is important for modeling and decision making. And also, they have to have a high mutual algorithmic information with the world. So in a nutshell, the theory asks what is structure experience in an algorithmic context, and answers that evolution has given rise to some things called agents that run models of the world with an objective function. They have goals, and this combination of model structure and valence that they carry gives rise to structure experience and emotions. So an algorithmic agent, in short, is a computational system that interacts effectively with its environment by planning actions using compressive predictive models to maximize an objective function. Using a model entails, again, computation and dynamics. Here is a more detailed view of this, but I won't go into this. I have another talk tomorrow, so I will have time to discuss this. But the central hypothesis in the theory is that an agent has structure experience to the extent it has encompassing and compressive models of the world to interact with the world. And more specifically, that the event of structure experience arises in the act of running these models. The structure of these models, which are algorithmic entities, mathematical entities, gives rise to the structure of experience. And that the successful comparison of the model predictions with data gives rise to what is called wakeful presence. Now, how do you define model structure is the next question. So here, I won't go into this now, maybe some more tomorrow, but you can formalize what this is in terms of group theory, talking about symmetry, and you arrive to the conclusion that the dynamics that are generated by these models collapse to reduced manifolds. So if you take EEG data or fMRI data, you find that the data itself is not in an infinite dimensional space, but it actually collapses into manifolds. And this has to do with the symmetries that are imposed by the world on our models. And one can picture metaphorically what structure experience is with something like this. You have some kind of crazy attractor that corresponds to your model of the world, and you're visiting some particular region of this model of the world right now, which gives rise, the geometry and topology of this particular region in model space is what gives rise to your structure experience. This suggests that you can use tools such as topology and group theory to characterize these manifolds that we can infer from EEG or from fMRI. There are tools that are mathematical tools to do that, that can be useful. AI can contribute by giving you the latent space and the manifold reductions that you need to start with. The second one is computational modeling. So here the aim is to gain a mechanistic interpretation of brain data using whole brain computational models. The brain has to be able to do these computations. This predictive processing is kind of one of the requirements, including criticality. So in summary, we focus on the requirements for structural experience. EEG, MEG, TS, TMS can all be used in principle to measure and alter structural experience in the electrical brain. Tracking the world requires computation to run models, and this ties with the ideas of criticality. This constrains brain structure and also collapses dynamics to reduce manifolds, the characteristics of which are good candidates for the neural correlates of structural experience as opposed to consciousness. If you're interested in these topics, there's a special issue open, which I am co-editing, on the mathematics of structure experience, exploring dynamics, topology, and complexity in the brain. And thank you.
We have time for maybe one question.
One question? Yep.
Any burning questions? There's one. You might have to yell it out.
Oh, there's a microphone.
Hi. So I'm wondering, because you mentioned all these possibilities for BCIs, like thoughts to computer translation or brain-to-brain communication. And I'm wondering, are there any limits to what EEG can do in the times of being a precise measurement of the brain? Because I'm just trying to think, whether within all these wavelengths you will have enough number of discrete, wavelength patterns to describe the whole vocabulary, for example?
Yeah. So 2 comments on that. So the first one is that EEG, I am assuming from the beginning that EEG and these electrical fields that the brain generates are actually what can give you the neural correlates for structure experience. The whole formalism is based on computation, and computation may also refer to quantum computation. It doesn't exclude that. So maybe that with EEG we are not capturing enough information. The other comment is that there is a mathematical theorem that says that if you have a nonlinear dynamical system of very many dimensions, and you actually sample just one channel of that system, if you have enough data, you can actually reproduce the dynamics of the whole system. So in a sense, if the neural correlates are in EEG, in principle, we should be able to collect them with our EEG systems. But if not, then we will be fishing out of the right place.
All right.
Yeah, one follow-up question. So you mentioned that if we have enough data gathered, so I'm wondering whether it will be always AI learning our patterns, or do we share some similarities when we are thinking the same thing?
That's another very good question. I don't know the answer to it. Personally, I think the future of BCI is personalized BCI. But it may be that we share a lot of these structure dynamical systems to some extent, and we can actually compare them and make sense to it. There is some work, for example, that shows that color perception between people, you can put color perception in a network, and you can show that across cultures and across people, you can actually find the same structure in the relational structure of color schemes that we have. So this gives some hope that we do share some things, and that my green is like your green. But I think the future probably will require to collect a lot of data from individuals, from a given individual, and then build their own interface. I actually have a short science fiction story on that, if you're interested. So.
All right. Thank you.
Thank you.
Appreciate it. Thanks, Tom. Okay, next up is me. So far you've heard, you got a nice overview from Tim on the different types of energy modalities where you can read and write from the brain. And so far we've heard about EEG, the electrical modalities, which is by far the most studied and developed. But there's other energetic modalities using light and sound primarily to try to read from and write to the brain as well. So I'm going to talk about ultrasound in this talk. I think in the next talk from Anirban, you'll hear a little bit about megahertz frequencies as well. And then we'll hear about light at the end. So for the past couple decades, there's been the development of using focused ultrasound mostly to modulate brain activity for neurostimulation. And what's relevant about this relative to what you've been hearing so far is the ability to focus across the skull into the brain and to target relatively specific brain areas, especially deep brain areas, which might be relevant for studying consciousness specifically. And so our lab for a long time, ever since Stuart Hameroff told us about ultrasound back in 2011, I think, 2012, we've been developing this at the University of Arizona, and it's been developing at lots of different universities and now different companies around the world. It's a very exciting space. And we know from the animal literature that if you focus through the skull or take the skull off, you can get hyper-resolution focus in the brain. So as you go up in frequency, the fundamental frequency of the ultrasound, so above a megahertz, you can get sub-millimeter resolution in the brain. The skull becomes a problem, which I'll talk about in a second. But in the animal literature, suffice it to say, when you modulate or stimulate the brain, you can get tail or whiskers to move in the animal. You can focus, in this case, on the thalamus and reduce evoked potentials, thalamic evoked potentials. So very clear from the animal literature. And what's happening right now is this is being translated into humans. And folks are trying to figure out how to get the beam across the skull to get these types of effects in humans. One of my favorite results comes out of Sanjik Yu's lab, where they focused into V1 of the visual cortex to try to induce visual phosphemes, so basically a visual hallucination. And if you push very gently on your eye, you'll see what are called phosphemes. They're these little moving geometric patterns. Actually, each one of you will have a little bit different pattern depending on the way that your retina and your visual cortex is organized. But basically, they were able to induce these just with the focused ultrasound beam into the visual cortex of that patient or that participant. So it shows the power of both focusing it, and it shows the ability to induce different conscious percepts. And as I said, Stuart Hameroff actually was one of the first to do this, actually the first to do this in humans back in 2012, 2013, and really opened the field, which is now a massively growing field all across the world. So Stuart was literally the first person to put this up on his head in the OR. And I was working on deep brain stimulation at the time with my PhD advisor and trying to figure out how to do deep brain work without drilling holes in people's heads, because although Stuart worked in the hospital every day, I didn't like going to the hospital, so some people were built for that. And Stuart figured out that you could actually use ultrasound to modulate mental states. We replicated that across about 300 subjects in a bunch of different studies. And what's really exciting about this as Stuart got into this, because it might be a way to test the influence of microtubules or the relationship of microtubules to conscious states. And we've gotten to the point now on the tech side where we can focus these beams into the brain with high precision. We now just need someone to measure microtubule activity in real time. And I'm looking at Anirban in the back of the room because he might have a talk coming up next about how to do that. So that's a really exciting way to test ORC-OR. I'll talk about this tomorrow, so I won't say much now, but our lab's been using this to modulate the default mode network by targeting the posterior cingulate in the brain. I have a plenary talk, I think, at 11 tomorrow, so I'll talk about that work in detail. But basically what we've been able to show is this is a very useful tool for causally manipulating temporary mental states. So in our lab, we're really interested in mindfulness meditation and the deep end of mindfulness practice. So what happens to consciousness and well-being over time, and how do the traits shift? And ultrasound has been a great tool to test some of the networks and brain regions that we believe are functionally relevant for long-term change in meditation. And now, for the first time, we have the ability to use this tool to actually causally test some of those theories. As I said, one of the hurdles here is that this is what you'll see in the literature, so a nice focused beam of sound. The red region is what should be modulated by ultrasound in the brain. The truth is that the skull acts like a defocusing lens, and so before this is a really high precision modulation and then looping it to a BCI system, this problem has to be solved. And actually my company and a couple other groups have been working on trying to solve this problem. We have a booth and our tech here today, so this is one of the first places where we'll be able to show this. This is a company I co-founded with Tim, who gave the beautiful intro talk. And using a little bit of AI and modeling, we've been able to solve that skull problem, which now unlocks the potential to now do highly focused, highly targeted, individualized treatments and stimulation. But that really sets up the whole system for doing closed loop and brain-computer interface looping. And in setting up this talk, I went back and looked at the literature using ultrasound for BCI. So last time I looked at this was about a year ago, and there's been a ton of work in the past year on specifically making ultrasound neuromodulation systems into BCI systems. This paper is probably the best overview of the current state with this really slick graphic that they made. And basically the idea is that you're using ultrasound mostly to modulate or stimulate the brain, and then you're either reading with ultrasound as well. So ultrasound's an imaging modality, as you all know. You can actually image the brain with it as well if you solve that skull problem that I was talking about. And now with real-time processing, like with Tim's company, Entheon, and others, you can process that information in the cloud and then feed that back to stimulate different networks in the brain. And so just with ultrasound in and of itself, there's lots of different ways to image the brain, and there's a ton of work going on in the literature around this. So you can image blood flow in the brain. You can actually do functional brain imaging with ultrasound, believe it or not, using transcranial Doppler, all the way to using ultra-fast, ultra-rapid ultrasound images, which, as Tim said, the technology has really taken off in the last decade to decade and a half, where now we have microchips that can process fast enough to do super ultra-rapid ultrasound imaging, so thousands to tens of thousands of images in a second. And then what you get is in the bottom right. So what you see down at the bottom, functional ultrasound localization microscopy. This stuff is really cool, and I have a bunch of images here. So all of the images you see here are basically microscopy and histology images that are taken with ultrasound itself. The caveat, this is in animals, and you've had to take the skull off at the moment, so if you don't worry about the lensing problem, and you can increase the fundamental frequency to like 10 to 100 megahertz, you can get these hyper-resolution, really beautiful images. This is like 10 to 100 times the resolution of an MRI. So this is all being demonstrated by a group in France, actually, who's doing a lot of this work. But as Tim showed that curve, I was sort of thinking into the future. When are we going to put the sort of ultrasound in the human brain doing this level of high-resolution functional imaging for a BCI, and what could you do with a system like that? I mean, if you had the structural, the functional, all at the same time. So this is all coming. This is why Tim and I founded our company in the space, and this will be really exciting to watch. But I also think it gives us hyper-resolution BCIs to start testing, on a sort of spatial scale, but also on a network level scale. We can start actually testing in real time and causally manipulating these networks to test some of the theories of consciousness. And then finally, I think in both Tim and Mai's heart is really getting the closed loop stimulation. So you heard a little bit about that last time. And ultrasound being mechanical waves, it doesn't influence the EEG or fMRI signal, MRI signal all that much. And so it's sort of great tech to combine with something like EEG, which is actually, you saw Tim stimulating my brain probably 6 years ago at this point with an EEG ultrasound system. And so there's a lot of work going on this in the animal literature. This is just one that I'll show you. So this is an induced seizure. So they're just recording directly from the cells that are seizing. And this is what happens when you do a closed loop ultrasound stimulation. So the EEG is waiting for the seizure signal. And then the ultrasound is targeting those neurons, the locus of those neurons, that group of neurons. And then basically you can see the seizure starts, and as soon as the ultrasound turns on, it usually takes about 500 milliseconds to a second, and you can disrupt that seizure activity in real time. So obviously, once you translate this into humans, this would be a big deal. And really, you can do it with just a couple channels of ultrasound and a really relatively cheap ultrasound transducer. So quite exciting. There's been a lot of other work if you're into neural oscillations, which we heard about previously. They've basically shown just in the last couple of months that you can use ultrasound into the hippocampus to drive the theta-gamma coupling in the hippocampus. And so when you start thinking about the relationship between these neural oscillations and theories of consciousness, now you can start manipulating and driving some of those oscillations in real time. And then finally, this is sort of where this is going. I was thinking about your slide, Tim, about the ethics, and I always feel weird seeing rats and mice wearing these things that are attached to their heads. I started in a rat lab and moved to humans for this reason, but anyway, I put it up. And so what's happening right now are these wearable closed loop systems. So this is EEG with ultrasound basically in a hat, but it's not really a hat because it's screwed to his head. And with this, you get hyper resolution again, and you can really modulate behavior in real time. So they're looking at mostly spatial navigation in the beginning, because we've mapped that system pretty well in the rat and the mouse. But it really shows you where this can go once this is non-invasive, and once we don't have to strap this to humans' heads. We can have a nice baseball cap. Maybe it looks like something like the Neuroelectric system, or maybe we just partner with Neuroelectrics, and now you can imagine a nice wearable system that's actually helping patients in their home. And finally, I just learned this. So the National Science Foundation just gave a big grant to Vanderbilt under the career program. I'm not sure what that is actually. But this is a wearable ultrasound system that has open source EEG. This is Open EEG, or Open BCI is the name of the company. And this is geared towards making a system that's very scalable, very cheap, and it's geared towards closed loop stimulation. So it's pretty cool to see this happening. There's actually 5 or 6 other groups doing something similar. And so Tim already showed this image. This is an image that Tim made a while ago. And so when you're putting all this together, what's exciting about it is now you have the ability to read brain signatures in real time, ultrasound targeted into the brain. And I think I didn't mention is that if you have multiple transducers or a multi-element array, so if you have like a 12 by 12 transducer, you can not only target one hub, you can split the beam into many different target regions simultaneously. You could even get sort of sci-fi with it and trace a network in the brain in real time. So basically you're limited by your ability to measure the brain activity at that rate. And so this gets really exciting really fast and really becomes an interesting tool for this type of community that wants to test theories of questions about what does the brain have to do with conscious states and testing those in real time. And finally, I would be remiss not to mention Forest Neurotech. So there's a lot of interesting companies besides ours coming in the space. So there are companies trying to minimally implant, so under the skin, above the skull. There's other companies implanting the transducer under the skull. If you go under the skull, you can do hyper-resolution in the human brain in real time. We're talking sort of, if you increase the fundamental frequency high enough, you could get down to the level of the receptors themselves. So this gets like really, really fine resolution. So there's a lot of this work going on, mostly on the West Coast right now, and I think we'll see tools coming out that are mostly geared towards neurological and motor disorders in the beginning, but it sort of sets the stage for where, in 50 years we're going to be talking about, or where kids are going to be talking about. And this is we're only at the beginning of Tim's curve in his last slide, so it's really exciting to see this develop. All right, thank you. Oh, I'm not going to give you those. I won't give you the caveats. There's a bunch of caveats, but I won't bore you with them. Next is Anirban. So Anirban, I'm hoping that you'll show us a way to measure megahertz resonance in microtubules, because then we can use our ultrasound system to modulate that in real time. And here you go. Yeah. Yeah, while he's setting up. He's asking with the hyper-resolution ultrasound, the ultra-fast imaging, what are they measuring? Mostly structural imaging in the beginning. But there's a researcher at our University of Arizona called Russ Whitty that's using photoacoustics and acoustoelectrics. And if you combine the two technologies, you can actually measure in any scale of electrical activity. So from the local field to, to the EEG with that. He's done a lot of work in the heart first, using ultrasound to measure current source dipoles in the heart. And if you go look up the experimental ultrasound lab, you'll see these beautiful, he just gets the whole dance of the heart electrical field as it's pumping. So it's all possible with it, but you got to combine it with EEG. Okay, Anirban, you ready? Great, thank you.
Okay. So this is a very, very technical session, and I really love it, the way it is going. A little different than consciousness. So I will talk about a few rhythm in the unconscious state that we measured. The work is primarily done by Pushpender Singh and Ashwadeep Atawale at IIT Mandi, because from NIMS Japan, they are actually taking over. And Tanusri Datta from IIM Ranchi, Dr. Shaifullah Tipu, who's supposed to present here, but his mother is terminally ill in cancer, so I'm presenting. Sarika Katiyar and Shanti Banishetty, Stuart Hameroff, and me. So last year in TSC, when I gave the presentation, I told that we are planning to do this work in hospital. We wanted to measure. And this year, we have published 3 papers, and I'm going to put the summary. So far you have heard about EEG, and in the last talk, Jay, you understood that multimode characterization of brain signal is necessary because Jeremy has told that he explained very nicely why the brain signal measurement is a very difficult challenge, and mostly you get artifacts. So DDG, duodecanogram, is an alternative to EEG. So duodecanogram, duodeca, that is 12. So you can see in that there are 12 cables each side, so there are 34 sites. So 408 sites simultaneously capture. And today I will tell you why this technology is very different than normal basic current voltage or other kind of characterizations. So Saifullah TPU is blue. This is the whole in the hospital, the team who had worked. And Sharika is with the red arrow. So the main result that we got was, this is from our paper in 2015-2016. We took, you see the probe, that is patch clamp. So you can, it is a glass tube. You patch with the membrane of a neuron, and to the right, there is a coaxial probe, atomically sharp needle, and with a amplifier. So high frequency signal, you need immediately an amplifier to amplify the signal. So we insert the probe in the microtubule bundle, and we measured around 0.18 millisecond with time width. This was 2016 result, and this is 2013 result, and you can see that the signal frequencies that we got after anesthetizing the human subject in the hospital is very similar. So similar kind of pulse train came. So let's see. So this is in the kilohertz. This is me, but don't think that I did most of the experiment. This is just, I got a lot of courage, and the operation is going on in this side, and all the anesthesiologists are there, and you can see that in the kilohertz domain, you see some kind of burst, and you don't see this burst when the person is awake. This is megahertz range. So you will see the burst is coming up, and when the person wake up, then you don't see this megahertz burst that we measured, and similar to microtubule bursts or microtubule bundle bursts that we did several years back, 7 to 8 years back we published. And so this is also our old work where we changed the length of the action to understand the origin of this megahertz burst signal that is coming up. And we try to correlate that the burst that we are seeing might have been coming from microtubule bundle. Now the question is, how come I still can't believe that signal can come deep inside my brain, penetrating the skull and come to the top? It's very difficult for me as a physicist, very, very difficult. Because when we were kids, our teacher used to tell us, if you switch on the light, does the electron flows? No, electron can never flow. It will take thousands of years, millions of years for an electron to go from the switch to the light to lit the lamp. Then what goes? Is electromagnetic field that moves. So how come some ions, some neurons in my brain is firing, and that ion is coming and sending the electrical field? If you take a glass of water, or some glass of water contains a lot of ions, try to send electric field from one direction and try to measure in the other direction anywhere, you will find electrical potential is distributed. So even if you deep inside my brain, some electrical potential is generated, how come it goes to a particular direction and sent on a particular probe? So it has been very difficult. So in our paper, Journal of Multiscale Neuroscience, we took 14 layers of all the layers that an ion has to pass through, or an electrical potential has to pass through, and come to my head to give the signal. I'm not saying that, I'm saying that all the EEGs are wrong. I think that even for DDG, the high frequency signals also coming out is very, very difficult. Very difficult. There could be other reasons, other origins. I just want to ask questions, because if we don't ask, we'll never get to the truth. So we did some simulation. We found that 6 to 26 megahertz, there is a possibility that the signal could come out. Not the full signal, 40 to 45% of the signal will come out. But electrical potential, it's very difficult. That was the foundation of starting DDG. So what is DDG technology? First, it does not measure the potential from the brain. It does not take any average, or it does not correlate different regions. So all the 6 parameters, if you search in Google, why there are, less credibility for EEG. Many people working for 15, 20 years with EEG, they ask questions about the credibility. Like particular emotional state, different people have very different kind of reactions. So in DDG, we have very short pulses. And suppose your brain is generating a signal, that pulse with a logic analyzer, it starts counting, and when it ends, it ends. So with a very high resolution, the emergence of potential is measured. So phase gap between different signal is reliably measured, and the distribution look like this. And basic mechanism over there, to the top right, the circuit. So you have multiple different comparators. So the electronics by which you measure for EEG is very simple, very, very simple. If you break the probe, you will find an anchor-like thing and a cable. But for DDG, it's very, very expensive, and you need massive graphics hardware and logic analyzers of a very good kind, ultra-fast pulse generators, comparator array, and large number of machines running in parallel. So for an example, for 12 different bands for dodecanogram, the 12 different time domain we want to look into. So we have 12 different machines, and each machine, 34 cables come out. So 34 different bundles come out, and each bundle have nanoparticle or quantum dot, core cell quantum dot structures at the bottom, using which you take the signal out. And the output that you get is almost like distributed density matrix that you measure in quantum. So if you want to measure density matrix in a quantum computer or in a quantum system, the protocol that you use, exactly the same protocol has been used in DDG. And the output is almost like 3D Wagner surface, so or density matrix or tomography. So let me show you some of the results that how it looks like. So in quantum tomography, what you do, any kind of quantum technology, if you want to build, first that you have to show is density matrix. If somebody doesn't show density matrix or Wagner function or does not do quantum tomography, then he has not measured it. He doesn't understand what it is. So this is the very basic, how the psi looks like. So how the psi looks like, you have to at least say. So that is top right corner is the density matrix. And when you have different kind of signal that is generated in the brain, you get this kind of star-shaped network that you are seeing, interference enhanced SG or SG gauge or squeeze, or this kind of potentials distributions you saw. Now let's get back to the results. So when we were doing the measurement in the hospital, the first thing that we saw was how it is different, the frequency distribution. All results are 6 to 26 megahertz, because we believe there is at least some possibility, 40% possibility of that kind of signal to come out. Signal to come out. So in coma, several patients who get brain hemorrhage or different kind, because we wanted to understand, I don't want to say, but I wanted to see when a person is dying, then what happens to the triplet. Because triplet of triplet, I have given so many lectures, I do not want to get into that details. So in GCS3, just before death, you have only one pick. One of the triplets survives. And GCS8, you have two of the triplet, and one goes very, very high. And in the bottom, just have a look at it. We anesthetize the patient, and we observed which part of the brain actually the megahertz burst comes in, and which part of the brain it disappears. So we wanted to understand. So basically, I hold on to the bed of the patient, and they were, in India during operation, it's like very crazy. They push the patient in and take the patient out. Doesn't allow him to get fully conscious. Okay, so it's not like Europe or America when we have less population, you get long time in the operation theater, they take, push and then take out. And then I hold on to the bed. I will not allow you to go until I see where is the last place where the consciousness comes. And then I found it here. So that result is here. And you will find that with the time lapse, those who have no experience with the B's values, anywhere in the hospital, operation goes on. When B's value goes to 40, 45, that region, operation starts. And operation ends, and then they allow the B's value slowly come up. So today, I'm going to tell you about this very interesting phase 1 and phase 2, deepest part of unconscious state. What happens there? So this is coma. And I checked all over the body, how triplet changes, how electromagnetic radiations has a very, very unique features and in different, especially in the spinal cord region, the features are very different. And yes, so these are the two slides, next two slides, are the message I want to give you. That when there are bursts that you are seeing, that is the signal the person is anesthetized. But you can see that sometimes when you are deepest level of unconsciousness, then these are the 15 phases of rhythms run at phase 2. And what happens is slowly the burst covers up 1, 2, 3, 4, 5. Then emptiness starts emerging, the silence. And that rhythm goes and complete awake and phase loss. So you see that between dead and awakening, there is another phase. This is another patient, and in some different medical condition. So you see the bursts are generating and moving, 1, 2, 3, 4. And then slowly the empty space fills up, and the burst goes to the nearly awakened phases. So what I want to tell is that this is the rhythmic cycle of various different kind of transition between various different conscious states that happen as in the deepest unconsciousness levels. And you saw what happens in coma and near death, just before death. So all these things gives the conclusion that we are just starting to understand consciousness and unconsciousness states. The triplet of triplet, I gave several presentations on that, is a mere upper surface, crude way of determining the level of consciousness. Consciousness and unconscious states are very different, and at a different level, you face very different kind of situations. Finally, one last story. What is the use of DDG? And I found the burst that is the signature of unconsciousness. And I was standing in front of the patient, and I found the person's this burst disappear. This level remained same. Doctor saying patient is okay. I'm saying patient is not okay. Patient is awake. At the deeper level of consciousness, I find consciousness levels. And then doctor went and checked the blood sugar, and blood sugar had fallen to 42. Immediately they injected sugar, and then sugar level came up, and I found the person is slept again. So you have many different layers of consciousness, and if you have a danger, some level wakes up, and you can solve the danger and then put him into sleep. So that's why my dream is to put, we saved 2 patients immediately when I was there, and after that they saved several patients just by looking into the megahertz bus. So that's why I dream that one day DDG will be there at every single hospital in the world to save patients from hyperglycemia and unwanted diseases, because who knows in which consciousness level you are sleeping and which consciousness level you are awake. Thank you.
Thank you. That was awesome. Thank you so much, Anirban. So we have 2 more talks. I think we're switching to light. Are you talking about your work with light? Yeah, and wearables. So this is Santosh. He's been doing lots of amazing work also in measuring consciousness in a really radically different way. So today he's going to be talking about some of his wearable tech. Thank you.
1, 2, 3. Is it? Okay. Well, thanks for inviting me, Stuart, and everybody, the organizers here. So what I'm going to tell you about, I've developed 3 devices, different kinds of devices. I'm going to tell you about 2 of them, which brain-computer interface is not my field, but the devices that I've developed could be integrated to produce a brain-computer interface that would have medical applications. So what I'm going to show you is data on the 2 devices that I've developed. On one of them, I'm going to give a plenary talk on Wednesday, so I don't want to go into great details. I'll just give you a brief overview of it. The second one I've not talked about at these conferences, so it will be an introduction of that device, and I'll tell you a little bit more about that. Next slide, please. Oh, do I have the clicker? Yeah. So this is if I were to be a person who develops brain-computer interfaces, which is probably more relevant to Tim and to Jay, is I have a plan of how to integrate 2 of my devices in making a brain-computer interface that would have very crucial medical applications. So it's a plan of a composite BCI system involving consciousness measurement and stimulation. And the consciousness measurement device that I'm going to talk about is completely new. It doesn't have anything to do with EEG, electrical activity, and I'll tell you a little bit about it, but more about it on Wednesday. So the plan is continuously measure the level of consciousness or content of consciousness using a variable, non-invasive device, right? In disorders of consciousness, in psychiatric disorders such as major depression, and in severe acute or chronic pain, obtain a readout of a specific biomarker in these conditions, and then non-invasively stimulate critical brain areas using a multifocal neuromodulation device or with a variable device to treat the condition. And it could be focused ultrasound or anything else, but I have a particular one that we have used in our studies, which we have developed ourselves. So that would then could be triggered automatically, for instance, in disorders of consciousness, or it could involve biofeedback, a closed-loop feedback system. For example, in pain, where patients might, you read out how deeply in pain a patient is, and then they would stimulate themselves to feel better and to let the biomarker disappear, right? So that's the thing. So the 2 devices that I'm going to tell you about, first is it's a consciousness measuring device. It's called the sentiometer. That's the name we have given it. And this is the prototype. By the way, all of my device development is highly low-tech, not the high-tech things that you have seen, including Anirban's talk. So the circuits are simple. The type of things that we are measuring are pretty simple. Of course, computationally, we can extract a lot more information than what I'm going to show you here. So the first one is the sentiometer, which measures consciousness. I'll show you how. The second one is called, it's a TMS, a transcranial magnetic stimulation device, but this is a portable device. It's a cap that you wear. And instead of an electromagnetic induction induced by passing a large amount of current to induce stimulation in one site, you have multiple high-field permanent magnets that are rotated rapidly to induce electrical activity. And it also works through a different mechanism, which I'm not going to go into here because we have done a lot of work to figure that out. And it can be triggered using an app on a smartphone. Okay, so I'm going to first briefly tell you about the sentiometer device, and I'm going to tell you more about it on Wednesday. So it basically has a microcontroller box, there's a sensor unit, and again, it can be interfaced even wirelessly with a tablet or a laptop. So the way, the motivation for that device was Roger Penrose's work and Stuart Hameroff's addition of microtubule substrate to it, which basically involves conversion of waves into particles, right? And then we think it's delocalized electrons inside microtubules, but potentially it could be anywhere. It could be mitochondria, it could be DNA and RNA. We don't know, but basically the essence of it is conversion of waves into particles. And there's a lot of circumstantial evidence, which Stuart has talked about, like the benzene ring structure with delocalized electrons floating around, and forming resonance, wave resonance, spreading resonance. I've been thinking about this for a long time, and I thought, purely, so basically we're talking about waves turning into particles, and the best system that can do that, or we can measure using it, is interference patterns converted into, with a double slit apparatus, converted into two bands, because, a tendency to form two bands from an interference pattern. And so what we thought about was, if the electron conversion from waves into particles happens inside the brain, you need something a probe that could measure it, and obviously there's no probe. There has to be a really sophisticated quantum probe, which nobody has invented right now. So I thought maybe we could generalize the hypothesis, maybe completely in a very speculative manner, right, and see if that works. I mean, physicists in the crowd will probably go crazy, it's because completely outrageous from their point of view. But what I thought was, if there are collapsing electrons from waves to particles deep inside the brain, what if that collapsing influence of those electrons spreads out in the brain, in the body, and out into the space surrounding the body, what we call the perisomatic space? If that happens, and if that influence not only is confined to just one wave function, which is, say, electron, but it actually able to influence light waves and collapse light waves into particles, then something like the double slit apparatus brought close to the head would be able to detect that. And that's what we did. So basically, we have a target where that target is shown, where you put the device in and you measure the influence of something that goes on in the brain, right? So we developed a device where this was, initially we tried the double slit apparatus and it worked, but now we have sort of simplified the device and we are just measuring beam diffraction. So there's a laser light being shown by a laser LED, and there are off-center photodiodes around the laser spot. And those off-center photodiodes are measuring how much light is diffracted. And so if light becomes particles in this situation, then you should see a decrease in the diffracted pattern, right? So the diodes that measure the diffraction should show a dip. And so now if you bring this device in a room, empty room where nobody is there, none of my lab workers are there, you get a straight line. If you have 4 channels, you get 4 straight lines. And if you make, take an average of it, you get an average. We take what is called we do a principal component analysis and take the first principal component, okay? But if you bring a person close to, or the sensor of the device close to the head of a person, you see a nice dip in all 4 channels, which if you do a principal component analysis, first principal component, normalize it with respect to the first time point, we can invert it, and you see something that looks like an excitatory postsynaptic potential from a whole person, right, which you can see there. And it is dependent on, so it falls off with distance. So if you're 1 centimeter away, the sensor is 1 centimeter away, you see a large response. If you're 16 centimeters away, you see a much smaller response. You also see the response not only from the head, because this whole thing spreads through the whole body, you also see a peri-manual response. So you could put your hand on top of it and see that response. We also, I mean, for the skeptics, which we were initially, we did a double-blind experiment where somebody, there was a device that did not, there was a chair without with an inactive sensor, and there was a chair with the active sensor. Whenever the person sat in the active sensor chair, we saw a response. Okay, so now we have, I'm skipping through a lot of stuff which I'll present on Wednesday, including mouse experiments with anesthesia and all that. This is the most recent study we are doing, which is patients in the intensive care unit with brain damaged patients. So what we see is in a normal healthy person, you see a large response. It's actually in an intermediate range. And in patients who are brain damaged, unconscious because of brain damage, you see, like for instance in this case, a flat response, which slowly recovers with the recovery of the person when it becomes more conscious. In other patients, like for instance in intracerebral hemorrhage, where there is not much recovery in this case, you don't see much recovery at all. And there's more stuff that I'll talk about. Anyway, so we have something that reads out consciousness. So now I'm going to tell you a little bit about, I hope, okay, sorry, about this new other device, which is a transcranial brain stimulation device. We call it transcranial rotating permanent magnet stimulator, or TRPMS. It's TRIPMS. That's the short word thing is. Again, it's a rotating magnet at multiple sites of the brain. You can put them anywhere on a cap, so it's a variable device. Other thing also is variable, and I'll tell you why. And so you get an oscillatory field, which sort of is like a burst of neuronal action potentials, which you can get. We've done a study, a pilot study in, well, this is when you stimulate the primary motor cortex, you increase the frequency of spontaneous action potentials or spontaneous motor unit potentials recorded from the surface from muscles. So this is the basic thing. We've done a study in ALS patients, amyotrophic lateral sclerosis patients that are known to have increased cortical excitability. So we've shown that in the early ALS don't show an increase in cortical excitability as measured by our device, stimulating the cortex with our device. But in the intermediate stage, you see this big thing. We did both a cross-sectional study and a longitudinal study and confirmed the effect. The second study we did with this device is because the transcranial magnetic stimulator has been approved, the traditional one, the conventional one with single site, has been approved for treating depression, okay? And there are a lot of studies being done in chronic ischemic stroke patients. who have not recovered from stroke, to see if by stimulating parts of the brain, they usually stimulate one part of the brain, because they can only stimulate one. In our case, we can stimulate multiple parts, some of which are supplementary motor cortex, premotor cortex, and many other areas, including contralateral side, to see if we can sort of revive the surrounding region of the brain that is dormant in these patients or has been shut out in these patients, to see if we can somehow cause neuroplasticity and increase try to see if we can increase the function. This is an fMRI study. I won't go into the detail, but bottom line is what we found is initially there was, when the patient attempted to move his affected arm or did gripping movements with his affected hand, there was no activation at all in the surrounding area of the brain that was spared. But with 30-day stimulation, you saw very nice activity surrounding the lesion. So, and this was sham treated. The nice thing about our device is we can use a non-magnetic rod, or demagnetize a magnet and rotate it rapidly to do a sham treated control. So like do a proper randomized placebo-controlled trial. And this was a preliminary pilot study, but we're going to obviously do trials later. So the conclusion was it was very safe, well tolerated, and we saw bold activation, which lasted, and some recovery of the motor functions, which lasted for 3 months after treatment. Okay. So anyway, my TRIP-MS sentiometer BCI system would involve integration of TRIP-MS with the sentiometer in the same cap, or use a sentiometry armband. So the nice thing about this, you don't need to wear it on the head. You can wear it on the arm or as a watch around your wrist, because it's, this thing spreads through the whole body. And in fact, the study we did in the patients, which I'm going to talk about more in detail later on, was done on the hand, not on the head. Okay? So integrate sentiometric data acquisition and program TRIP-MS stimulation in the same microcontroller controlled by a smartphone app. And then continuously monitor sentiometric data and automatically trigger stimulation using TRIP-MS in DOC. Obviously, these patients cannot stimulate themselves. They're unconscious. But there have been studies that have shown that stimulating magnetically and deep brain these patients, you can actually might be able to wake them up from deep unconsciousness. And then we are potentially trying to establish a collaboration, with a person who is kind of the leading authority in the field. Then the fourth thing, obviously, is prescribed continuous monitoring sessions with feedback stimulation to achieve relief of symptoms of a specific biomarker in pain condition, but could be any other psychiatry condition that you can think of. In fact, there is a trial, another pilot study going on in our psychiatry department with these collaborators of mine. And I have collaborators in the ICU study, and the rest of most of the work that that I'm going to tell you about on sentiometry was done in my lab directly. Thank you so much. Yeah. Thanks.
Thank you. Very neat.
Oh, thank you.
All right. Last but not least, we'll have to go for the last one. We'll take it after this one. Yep. Last but not least is Lou Lim. I was going to be talking about photobiomodulation, so using light to stimulate and maybe read as well. You said you were going to talk about BCI, so it'll be interesting to see.
Okay, thank you.
Lou is a pioneer in the light photobiomodulation space. I've always admired his science, and now that I've worked on a couple of my own companies and with other companies, he's also a pioneer in getting this tech out to people. So respect him in both ways. Thank you, Lou.
Thanks, Jay. Thank you for staying back. I know the last one. Stay awake, stay fresh. So I've changed the title a little bit. You know, the original title on the program is Photonic Stimulation. Actually, photobiomodulation is a better word because we're influencing the biological system. And I'll touch on the other aspect of it. Now, so we're not talking, when we talk about light, sometimes in this conference, we think about biophotons. So it's not about biophotons. It's not about flickering lights in an environment. It is about light penetrating through your scalp and going to the brain, or in our case, up through the nose to the brain. So when I first started this whole project quite a number of years back, I get a lot of skepticism. How is light possible? How can you penetrate the scalp and all that? I will skip the established mechanisms about the mitochondria and electron transport chain, which is biological, but there's nothing like objective measure in an fMRI scanner. So we have this project that's actually still about to wrap up with the University of Toronto, and we are doing this real time. So we have 2 irradiation spots through lasers, one in the right temple, one intranasal. And we put the subjects, healthy subjects, into the MRI scanner and see what happens. Because when I first started, I was obviously apprehensive. You know, I've got this hypothesis, it's going to work. I've got people reporting. Then I'm wondering, is it anecdotal? Right, so we do this, fingers crossed. And so if anybody is still wondering about whether this is doing something to the brain, I think that's over. Now, we're fine-tuning this now. Look at this, we put this on these irradiation spots. Now, this is on 43 subjects. This was before we actually totally wrapped up for 45. It's a composite data. We had 2 different wavelengths, 808 nanometers, 1064 nanometers, pulsing at 10 hertz, 40 hertz. This is the transcranial data, and this is the data set intranasal. You may not see a lot, but actually the change is actually quite profound, both and for the 808 nanometers, particularly 10 hertz, and generally here, the composite data shows that 808 nanometer get more response out of the brain measured in blood oxygen level dependency. Now, intranasal was quite surprising, okay? When I first introduced intranasal, people were like baffled. But actually, this peak was at 150 milliwatts per square centimeter. This is only 9. And look at the response from the brain. Pretty profound, right? So I just want to leave that for now and just say that intranasal is actually pretty powerful at very low power. It draws, just through the nose, a whole brain response, both from transcranial too. Then, at the same lab, we did real-time EEG with 256 electrodes. It's a lot of pain. So the researchers really did a good job. So what did we see? Again, I would say the response is pretty significant. This column on 808 nanometers, 10 hertz, 40 hertz, that's 1064 nanometers, 10 hertz and 40 hertz. They're actually quite different. I was, intuitively, I heard people saying, if you deliver a certain intervention at a certain frequency, your brain is going to respond to that. Actually, it doesn't. Look at that. All over the map. What I draw from this is, again, response different, and it's really hard to predict. The wavelength matters, the pulse frequency matters, and when we deliver, let's say, this 40 hertz gamma, you'd expect a lot of gamma, but actually alpha is showing a lot. But 808 nanometers, is doing something really interesting. It is down-regulating delta, slow waves. So if you're kind of sleepy right now, do this, it suppresses slow waves. You're more awake, right? But at a different wavelength, 1064, no, it doesn't actually downregulate delta. It actually stimulates delta. And you deliver 40 hertz, you just stimulate 40 hertz. So now what do we do with all that? It's kind of all over the map, right? Now, the thing we found, we know that different frequencies are doing something interesting to the brain. So what we did is we have developed this device where we have more electrodes, more LEDs, and then we have this, this wireless interface on the phone to program it to do this sweep. And we really wanted to learn what's happening to the meditators. Actually, we were doing, before we developed these remote things, and we found that meditators are responding very differently. Now, this is the focus on long-term meditators, expert meditators, and we are finding this. I want to say that until I came to this and seeing this, wondering how this is happening, I wasn't sure about mechanisms of the microtubules. I wasn't sure about this effect on quantum physics. I've been following this work. So there's always this debate going on. Is it this, is it that? And it's hard for me to, based on reductionist approach, I say, okay, you got to be a resonance somewhere, right? So there's a natural resonance in these structures. You deliver this, and you get this resonance. And what we are finding is this. I'm saying that the very, very important thing you need to understand is we do this sweep, 40 hertz, 120 hertz, 432 hertz, 1000 hertz. I'll talk about a little bit more of our work. We actually have more detail on Thursday, I believe. Sanjay Manchanda was helping us, I think, with University of Arizona and University of Toronto. There is a frequency. They hit, quite often it's 120 hertz. They go into a jhana state, altered state. You hear more about it. You can try actually the devices at the booth. This is quite shocking. You actually literally get into a higher level of consciousness, put it that way, at a certain frequencies. So, what is happening? So we used 8 and 10 nanometers. You do a quick calculation, convert the wavelength into frequency, which is in the near infrared region. You come out to 10 to the 14. Now, where is that on Stuart Hameroff's? I really love this spatial temporal hierarchy. I love the word spatial, space and time, spatial temporal. And so where are we hitting here? And I don't have time to show quite a lot of investigations we're doing now, actually a lab on tubulins and microtubules. Come on Thursday, we show more. This is the work I'm doing with Jack Dudinsky. Now, so 10 to the 15 is actually going deeper than the tubulins, right? You're going to the dipoles, influencing the aromatic ring. I think that there's resonance happening here. You may argue, you're going to the brain, how do we know? But actually, we do have direct, because of time, I'm not showing that here, the effect on the tubulins and how it's polymerizing or depolymerizing into microtubules or out of microtubules. Then, and here are where the meditators are responding at the microtubule network and a bit higher. And they're very specific. So somewhere here, there's coupling. I cannot explain what happened in between. I think if you have resonance here, you're taking care of the deeper and more, small structure and going to the quantum realm. And, and here is, there's like what, you will do a search, you see what's happening in the brain when this is happening, I did a search, and you say, there's more evidence talking about neuronal synchrony than what I'm proposing here, but then this is all new stuff, So, a specific frequency, get a consciousness leap. Stuart will say, bing, right? That leap. Now, this is opening up to a lot of things that we want to investigate. And now there's richness in data. We have a lot of EEG. We are running through using machine learning to understand all that. And my passion, actually one of my passions is try to resolve Alzheimer's disease. We did touch on that. And this is the paper I published last year. It's pretty extensive, looking at the pathophysiology. And my proposition is that out of all this stuff we're discussing, I think maybe the path lies in using EEG as the basis to do artificial intelligence. And then we can do remote tracking, do telemetry to the cloud, go to a central computer. So these devices are wearable, and we have clinical trials coming up with the FDA. One is Alzheimer's disease, one is traumatic brain injury, where we will incorporate different frequencies plus monitoring usage at home. So come on Thursday, we'll talk a lot more because I haven't touched on the biological side. So I'm talking about empirical evidence. I won't be so good about jumping into hypotheses and debating about it, and I'll give you more empirical evidence on Thursday. Thank you.
Thanks. All right. Okay, thank you, Lou. Great. We're a little over. We were going to take a break, but I think we'll jump right into taking questions. I'm surprised so many people are still here. I guess it's almost 9:30. So we're going to go technically till 10. The speakers have said that they will stay as long as you have questions, so midnight at least, right? And maybe if you just want to join us on stage. Sorry? Yeah, go for it. Yeah, you guys can just come and join. Yeah, you can go ahead and join.
About the last talk?
We need one more seat, I think. 1, 2, 3, 4. Thanks. Yep, I think he has a question for you.
Thank you.
Go ahead.
Okay, so about the last talk on infrared stimulation through the nasal or this temple stimulation, would it be possible for the participants to feel something through the temperature change or some kind of, very low threshold visual kind of phosphine-like thing?
You actually do not feel anything. You can try these devices, which is quite surprising. You do magnetic electrical stimulation, you do feel a tingle or something. But this is just light. The beauty about light is it does its work. It's a quantum particle, so it doesn't have anything mechanical to push the stimulation.
I've got a question for Jay, if you're not too tired this stage in the day.
Good. Beyond tired.
Yeah, I believe it. I was curious to hear that Visual 1 TFOS stimulation generated phosphines, given that V1's mainly, as far as I understand, full of orientation columns. So I'm quite curious to hear if you have any information about what those phosphines were reported to look like. Were they black? Were they white? Did they have any weird ringing artifacts or things like that?
Yep, that's a great question. As soon as I said V1, I thought to myself I should correct it, because it wasn't just V1. They're sort of targeting V1, V2, and the inner cortex there for the visual system. Especially since I don't think that group was correcting for the skull, so that beam probably was widening a little bit. And they got it in about 75% of people. But it was very similar. I think they went back and checked, and it was similar to the phosphemes that they get by pushing. And that's suggestive that it is visual stimulation, because it's sort of depending on how your visual cortex is sort of wrapped in that sulcus, that's kind of defining the geometry that you see. It has been pretty hard to replicate. I've tried to replicate it myself. I tried for about 10 years and finally replicated it last summer. So other groups have been trying to replicate, and I think it gets to like all the parameters that we're all using here are quite open, and you know, changing these parameters just a little bit tends to really dramatically change the effects. So it's not a knock it out of the park effect yet.
Is there somewhere I can find those parameters?
In their paper, I also made a GPT for ultrasound study, so I can just send you the link to the GPT and you can ask it. It only hallucinates about 10% of the time.
Awesome.
Can I ask one more question about the ultrasound, megahertz, gigahertz, terahertz kind of activity evidence? I'm quite kind of impressed through in the comparison between the wake and anesthesia and things like that. But I want to see if is it possible to record something like that directly by, let's say, patch clamping the single neurons of the animal, culture or brain or something like that, and then not like the direct demonstration of the oscilloscope, but digitally stored all the data into the very high sampling rate recording and so on, and then to do more kind of proper quantitative analysis. Has anybody done something like that? Does anybody know?
Not that I know of. I think Anirban may have gone to sleep.
Can I answer that?
Yeah, go for it.
I didn't quite catch it all now, but you can measure megahertz from the scalp easily, as he showed. And you can measure, obviously, hertz. You can measure megahertz, and now terahertz, photons, coming out of the brain in this photoencephalography, where the photons are buried in the EEG. So the only thing in Anirban's time crystal idea, where microtubules have hertz, kilohertz, megahertz, gigahertz, and terahertz, we've documented all of them except kilohertz. But in kilohertz, there's the Neuralink uses 20 kilohertz or 19 kilohertz to interface. So that shows that there's something going on with kilohertz. And gigahertz, I don't know, but all of these, as Lou showed, come from microtubules, which act collectively. So they're like a collective time crystal effect. So all these frequencies are coming out of the brain and allow things to scale up from very small to very fast. So one of my questions actually was to the panel was how do you account for kilohertz coming out from the brain? I mean, we think it's from microtubules as the other things. And then one question for Jay is, can you update me and others on the latest on ultrasound for Alzheimer's? You sent me some beautiful references, and including particularly unfocused ultrasound for Alzheimer's disease.
Sure. First question, kilohertz, maybe over Tim.
Well, I mean, one thing about kilohertz, and I mean, we sample at 20 kilohertz with pretty much any invasive device to be able to get, a complete action potential is going to be like 1 millisecond or 2 milliseconds. So to get the full time course of that, we're going to sample at something like 20 kilohertz or so. But there's also like things that are like sub-action potential, sort of sub-threshold oscillations or dendritic potentials, called like sub-threshold dendritic potentials. These are like fast little oscillations in the membrane that don't generate an action potential. I'm not sure, Giulio, if you know the upper limit of that, but it's definitely higher frequencies potentially than you're going to get with like action potentials if you're talking about one action potential every 3 milliseconds or something like that. So it's possible that you could pick some of those things up too, which are, there's a lot more going on than just action potentials at potentially higher frequencies in the electric field without having to necessarily, I'm not saying it's not, in microtubules, but.
Well, we know that microtubules generate kilohertz, so it's a good chance for that. So I'm curious about Jay, ultrasound for Alzheimer's. Anything new on that, or what's the literature?
There's a lot going on. I think in the review I sent you, there's about 15 papers. So there's been another 5 to 10 that have come out since then. The basic finding is if you focus the beam into areas where you have memory disorder, like hippocampus or entorhinal cortex, people are showing, so actually Sunchik Yu's lab at Harvard have shown that you can increase memory function. So it's not really slowing the disease down, but upping the cognitive capacity of the memory system. But I think what you were asking about is more of the unfocused ultrasound, so if you're sort of bathing more of the brain.
The disease is more than just in the hippocampus, it's all over the cortex.
Yeah,
so unfocused would be better.
Yep.
We think it is.
Yeah, so there's some evidence, and there's actually a separate literature where if you ultrasound a broken bone or if you get a tear in your skin, if you ultrasound that, it heals faster. So there's these effects on likely the inflammatory response when there's damage to a cell due to the ultrasound. So it sort of increases inflammation very temporarily and then decreases it over time.
So it's healing, and that could be through microtubules also, which is very important in the immune system.
Yep.
I'll shut up now.
So, but that's, lots of folks are showing that. I mean, people really haven't looked at those types of inflammatory biomarkers in the brain yet, but it's definitely happening. Yeah, go ahead.
Send me those other references, please.
Sure. You might have to remind me tomorrow.
Cool, hi. So I have a question for the second last presentation and also the last one. So the first question is, you were mentioning this like consciousness like measuring device, right? That's how I understood it. Can you expand on like how you were able to isolate that graph that you saw means like consciousness over, let's say, like just something else? And also, I remember you showing the graph where you show like someone that's like more conscious is, it's at a higher level versus someone that's like, that's a patient that's like a lot less conscious. Have you seen other parts of that spectrum? Like, I wonder what happens if you put someone on psychedelics, or what if someone's like got hit in the head, and are you, like, what does consciousness even mean in this case? Like, what is that y-axis?
So the answer to the first question, well, I'm going to present a lot of that background information in my plenary talk on Wednesday. But if you're asking if it's a non-specific effect, like a temperature, for instance, or some, radio frequencies, or sound coming out, ultrasound, ultra-weak photons coming out, or something like that, we have ruled out all of those things by doing specific experiments directed at each of those possibilities. I'll explain to that more in detail in my talk. For instance, simply, if you can do the same, you can put the whole device in a vacuum chamber and bring your head to the wall of the vacuum, and you still see the effect. So it doesn't require, cannot be explained by conduction and convection of heat, or sound waves, or air pressure waves, presence of any molecules floating around there that might carry it somehow. We've also looked at possibility of heat radiation causing, radiated heat from the head causing it, and we've ruled that out as well. So regarding the second question, what we have done, our study now is in the ICU-based study. So we're studying patients in the neuro ICU, in the medical ICU, and in liver and surgical ICU. So these patients have unconsciousness due to various reasons. Most critically, obviously, if you hit, if you have intracerebral hemorrhage or any kind of stroke, which leads them to be unconscious, that is direct brain damage. So a lot of that data, we're focused on that in particular, but we also have cases where patients have unconsciousness due to hepatic encephalopathy. So like they have liver failure, for instance, right, for many, many reasons. And we find very interesting differences there. And just briefly, for instance, hepatic failure patients can have what's called delirium. And delirium is a kind of a hyperconscious state, so to speak. Nobody knew about what kind of consciousness people with delirium have. We have found that in delirious patients, the amplitude is much larger in that waveform that I showed you compared to normal subjects. Okay, and then if you sedate those patients, those delirious patients are sedated. They are put on, a lot of these standard sedatives, including ketamine and even propofol, which is an anesthetic. We find that delirious patients who was having a very high amplitude response comes down. The response, if you record after the sedative is given, the response amplitude comes down. So it looks like we are measuring something that correlates with the level of consciousness. And obviously in unconscious patients, so like we had a cerebral encephalopathy patient, who was Parkinson's disease with dementia and had some acute encephalopathy. That patient, when he was brought in and put in the ICU, we recorded and we all got a flat response, which I showed you, completely flat response. And over days, he recovered. And as he recovered, we saw an increase in amplitude, which ultimately was almost normal. I mean, was actually normal level. And the funny thing is, the patient was still unresponsive, although the clinician determined that he is fully conscious. And so there is this discrepancy with treatment. Like one of the other experiments that were shown, results that were shown, had to do with using the zip and the zap method with the transcranial magnetic stimulation, zapping the brain, and then zipping the file to see the complexity, perturbation complexity of the EEG response that you get. Those kinds of studies, I don't know whether they'll catch the subtleties of these different consciousness levels and possibility of delirium causing higher consciousness level. So, I mean, it's complicated, and we haven't done psychedelics yet, but it is in the plan to do in the future. It's very difficult to do psychedelic research. There are very few labs that have quote-unquote permission to do it. So, we could potentially do it with ketamine, because ketamine is used as a treatment for depression, and that is something that I'll focus on next after the ICU. I mean, we are expanding the ICU study, so we will see some interesting results in that.
And just to clarify, when you say like higher consciousness, how would you define consciousness in this example? Does it correlate with wakefulness, or it's not correlate with, it's orthogonal to like wakefulness and neuroactivity?
So we just look at, one of the things I didn't mention is like we did it first in mice, right? So we found that the wave that I showed you, the EPSP-like thing that you see, its amplitude decreases with anesthesia in mice. And we've tried there's 6 different anesthetics we have tried. Propofol, the standard ketamine xylazine, which is given to animals. We've tried isoflurane, and we've tried pentobarbital, and one other anesthetic. So all of those anesthetics when you put the mouse under those anesthesia, inject those anesthetic or give them by inhalation, we find that the amplitude of the response decreases. So that's the definition of our consciousness. Whatever causes a decrease in the amplitude of the response suggests that there is some aspect of consciousness that we are measuring with this device. As far as the content, so I will have another experiment in my plenary talk. I don't want to give it away.
We have
now.
another question here.
Yeah, sorry. Yeah.
But, have you tried to publish this in the quantum mechanics journal? Because if this about your consciousness meter is right, then it would be one of the most revolutionary things of this conference.
I have sent a paper.
I said to it, I know you haven't because they won't publish it because they don't believe it.
Yeah, so
I believe that you have tried everything to rule out temperature effects and so on, but it is rather. It sounds rather amazing. It would turn some physicists upside down.
Yes, so I am hoping that there will be enough physicists interested in this phenomenon to test it. But I have sent the paper out for publication, and it's under review right now.
Okay.
Yeah.
Yeah. Well, I'm interested.
Yeah. Yes. I mean, if you are a physicist, you're welcome to try it out.
Oh yeah, thank you all for your talks. I really enjoyed them, all of them. And I'm super excited about neurotech and how to use it to increase well-being. I think that's the ultimate goal, really. And I'm personally most concerned with finding ways to alleviate the most severe forms of suffering, both psychological suffering, but also extreme physical pain, such as cluster headaches. And I'd be curious to hear whether you have any ideas on how to potentially use some of the technologies that you're developing to make a dent in this problem. And I believe, Santosh, you mentioned a couple of ideas, but I'm curious about others. Thank you so much.
Yeah, I mean, I don't know, I guess others.
I can.
Yeah, you have.
There is a stimulation method that's approved by the FDA to deal with cluster headache, and that's vagus nerve stimulation. So that's, I guess, you could try that. We actually developed a photobiomodulation-based vagus nerve stimulation. The ones that are out there are all electrical stimulation. We have a study that's coming up with Massachusetts General Hospital and Harvard. But that is to show that vagus nerve stimulation with photobiomodulation works. And the end point is, for that particular study, is stress. But I think, I guess I'm saying this because I understand this photobiomodulation really well. And we got quite a number of anecdotal reports. If you're looking for increased vagal tone or heart rate variability to mimic what's been approved by FDA, I think using light is a good way because other than what I showed you, light therapy, photobiomodulation actually has these healing properties above from just stimulation. That is very well established that it acts on the mitochondria, which equates to increased energy, and then increase the release of nitric oxide for vasodilatation, plus better gene transcription. So your body becomes what is supposed to be as a healthy body. So quite a number of things. So I think watch out for this space, that we're going to be involved in.
Wondering if Giulio or Arnaud has a...
Sure, I can comment on that. Yeah, we have good experience, and we and others have good experience now with TES applied to depression. We have some good pilot data, and which comes together with work from other people. Our approach is using multi-channel stimulation and try to really understand the mechanisms, for example, of depression. And that requires, I will be talking about this tomorrow, in fact, this requires defining what depression is to begin with, and because depression is a multi-etiological disease, so you have different types of depression with different causes and different circuits involved. But we have pilot data, and it's looking promising to treat that. And this is something that you can do at home, presumably. So yeah, there is hope. We're also launching work on the combination of psychedelics and brain stimulation. So the idea there is that these two technologies are highly synergic and can be used, especially in depression. Yeah.
Anybody else want to tackle suffering?
Yeah, I can mention something with respect to EEG specifically, and the fact that we need more measures which are calibrated to specific subjects. And I think that's where in BCI, brain-computer interface, pure control of cursor, you gain about 10 to 15% when you tailor the measure to this specific subject. So either you try to train an algorithm that's going to work everybody, or you try to train an algorithm that will work for that specific person. And you can do it in between too. But basically, yeah, I think that's a prime with the field. For example, for cluster headaches, you would need data from that person where they have headache, they don't have headaches, and then you can maybe tailor some neurofeedback intervention or some other, TMS or ultrasound intervention where you monitor with EEG for it to be efficacious.
Do you want to go, and I'll finish some thoughts? Well, I was actually going to refer to some of the stuff Jay does, because I think with things like transcranial focused ultrasound, there's real potential to target some of these brain structures that are maybe at the root of things like chronic pain or depression, anxiety. And I'm also reminded of Shinzen's equation of suffering equals pain times resistance. Shinzen Young is a meditation teacher that Jay works with, and a wonderful human being. The flourishing wheel I showed at the end of my talk was derived from his table of happiness. But when we think about that, like the pain times resistance, well, the pain you can't do anything about, right? That exists. It's a fact of your body. But the resistance you can do something about. And the equanimity that comes from meditation practice removes that, but also like Jay's work in helping to accelerate access to equanimity through brain stimulation can be one of the general treatments for various forms of suffering, whether it's chronic pain or whether it's depression, etc. In many cases, if you have equanimity, the suffering is not there, even though the rest is. So I think that's an interesting direction. I'd love for you to say more on that, but briefly I want to say one thing about inflammation and Lou's work, because I've started to over many years working with all kinds of different technologies for stimulating and recording for the brain. I've started to look a lot at neuroinflammation as like a root cause of a vast array of chronic issues, from chronic migraines and headaches to even depression, anxiety. People who have traumatic brain injury 5 years later, they have depression, they have anxiety, they have cognitive issues, they have pain sometimes, non-specific etiologies, almost all probably due to chronic neuroinflammation due to diffuse axonal injury. And so the photobiomodulation is one of the great ways to reduce inflammation in the brain. So again, it's looking at these root mechanisms, like what is the brain doing? We can rebalance neural networks, we can give drugs, that's even higher up. Rebalance neural networks. Even below that is like, why are the neural networks imbalanced to begin with? And if the brain is suffering from chronic inflammation or reactive oxygen species, you're going to have significant signaling problems all across the brain. So, yeah. Anyway, but back to suffering.
Easy problem.
Can I talk about inflammation?
Yeah.
So there is a paper that is under review right now, submitted by the University of Utah. And they actually studied, this is related to traumatic brain injury. Utah studied the college football team of BYU, Brigham Young University, neighboring university. So this was the season before this one, and they have a control group that just do the normal thing among the college football players, and the other one's the active. Now, other than the clinical assessment and the cognitive assessment, they actually did diffusion tensor imaging, which is totally objective measure. And watch out for that paper. I think I don't know when it's going to come out, maybe in a couple of months. Now, I mentioned inflammation because you can image inflammation with diffusion tensor imaging. And of course, the other thing they measured was axonal injury, which is like, the expected endpoint for TBI. They found that those who were on the active device before the biomodulation actually had no sign of inflammation at the end of the season, and they actually improved with what they came in with, which is, so for me, we've got a lot of work done within the photobiomodulation community about inflammation, but this is actually, this comes out of my mind. If you want to see objective measure, in college football players, level of inflammation is there. So one of the established I say outcomes for the biomodulation is actually reduction in inflammation.
Yeah, thank you. Yeah, I guess I would say just briefly, and I'll be talking about this a little bit tomorrow about our work. You might have seen on my slide, I had putting equanimity at the heart of neurotech. So that's been the sort of goal of the lab in collaboration with Shenzhen and Tim and a bunch of other people in Tucson is to, what I would say is, you know, as a people, historically, we've been working on the problem of suffering for a very long time and trying to understand the root causes. And I do believe that we've found methods to do that. They typically just are very hard to access, take time, maybe take multiple lifetimes, and then sometimes randomly people just wake up and are free from that chain. What's exciting to me right now is we are coming to understand the biology and leading towards theories of consciousness, which will radically accelerate the access to those methods. A, and then B, we have neurotech that's going to directly interface with the whole system, the whole sort of biological layer. And so when you add all that together, maybe sprinkle some AI on top of it, of course, because that's what's happening right now. You know, what that does is it accelerates people's access to what we've known for a long time, which is how to get to those root causes and free people from that causality. So it's quite exciting to me to be working on that, and it's part of Tim's, you know, so that's going to be on that trajectory is where, you know, at the foundation of creating access for the masses to something that I think will radically change humanity over time. And I think we have to do that right now because there's a lot of more potential suffering coming for this planet.
Yep. If I may.
Can I mention something on suffering? So I used to be a meditation researcher, and the goal of meditation is the end of suffering. And so then I realized, well, I don't need to be a meditation researcher. I can just focus on well-being, and then you cut the middleman. You don't need meditation. You just focus on the target goal, which is the end of suffering.
That is what I heard the Dalai Lama say at the Society for Neuroscience in 2005.
Oh, yeah?
He said to a group of neuroscientists, 15,000 neuroscientists, he said, someone in this room is going to figure out he thought it was a surgery, but maybe a chemical intervention that would get at the root cause, and therefore you would not have to meditate. And it was sort of controversial because he had ripped up what he was supposed to say, and that's what he said instead. Yeah. And they were trying to pull him off the stage, and he said, one more thing. I will be the first to sign up. So at least the Dalai Lama agrees with you. I'm not sure everyone does.
I was going to comment on the suffering thing as well, that I think it's very exciting now that we have all these new technologies to interact with our biology, brain stimulation, drugs, meditation, all this. But what we're missing right now is a way to connect third-person science with first-person experience. There's a huge gap there that we need to fill, and we need a framework that will allow us to bring the two worlds together, because at the end, suffering is about it's first-person experience. So if we don't have a theory on how that connects with biology or with circuits or with dynamics or whatever it is, we're going to be doing trial and error for a long time, as we have been so far since aspirin or alcohol or whatever we're doing now.
Yep. Yeah. 100% agree. And actually, if you've heard of the Mind and Life Institute, Valera, who's one of the neuroscientists who started that with the Dalai Lama, he was calling for neurophenomenology, I think back in the 80s even, saying that if we can figure that out, as you're suggesting, then it's going to accelerate that type of access.
Yeah, it's kind of a revolution in science that we need now, a new paradigm that we have. I guess if you have read Philip Gough's book, Galileo's Error, Galileo took the detour in the development of science of focusing on third-person science, observations, and all that, and left the first-person part aside because it's very hard. It's not because it's not important, I think. it's the most important one, but it's the hardest one as well. So I think maybe now it's time to try to bring those two branches together.
To that point, I think that there's a way I've been thinking about mental illnesses or mental disorders, clinically speaking, as disorders of consciousness or as altered states of consciousness. And, to speak to your point, I think maybe this is a rationale for why we should be studying consciousness, especially self-awareness, the construction of self. I really liked in your talk the differentiation between awareness, which may not be generated by the brain, and maybe the operationalizing of that through constructs like self-awareness. The sense of self, I believe the brain does produce, at least in the way we experience it, a very complex identity. Yeah. I'm not sure that plants experience self in the way we do, but I do believe that they have awareness. But in any case, that sense of self, that is at the root of things like severe depression, anxiety, schizophrenia, many mental health concerns we could see as being some kind of aberration of that construct. We can call it an aberration if we define normal as being, I'm happy. But so maybe this is the solution, as we understand how that works, and then that gives us the solution to the entire panacea of the plethora of different issues. It's kind of a panacea, maybe. Mm-hmm.
Anything else, or are we ending on suffering? Okay. Yeah, you have the mic, so go ahead.
To the panel as a whole, are any of you aware of studies out there or underway applying this to impulse control, the recovery from addiction?
Actually, there's people doing focused ultrasound to try to adjust this with targeting I think it's the ventral tegmental area, but maybe you can speak to some of this stuff. So brain stimulation absolutely is being used for addiction control today in various ways, and I think probably some of the most promising are deep brain targeting areas, which non-invasively would be focused ultrasound.
Which ones?
What's that?
What do they stimulate?
Ventral tegmental area, I believe, is one of the main targets. Yeah.
VTA, which I think they've also tried the deep brain stimulation as well, and works really well. You just have to do the brain surgery, and then I think over time it lost efficacy. So as the person had a stressful life event, the addiction came back. I think people have been trying TMS and TES as well, and
the
you guys have worked on addiction actually.
Dorsolateral prefrontal.
Left dorsolateral prefrontal cortex, that has been the area that has been stimulated in gambling, drug addictions, and there are enticing results there. There are some, one of these meta-analyses that indicate that there is potential there. It's one of the most promising ones, I would say, in addition to depression, epilepsy, and others. Yeah.
We actually have a study coming up in West Virginia for addiction. This is a hotbed for addiction over there. So initial results are pretty good. So now I think they got funding from the government and the state. So we're starting the study in the fall. Nothing.
I mean, honestly, though, the most compelling results I've seen recently are with ibogaine. I mean, one major dose of ibogaine at 80% of people with up to 6 months is the last study I saw, which is pretty wild. And I think one place that we've really been thinking lately is we get quite compelling results, especially with focused deep brain stimulation, but the time course is very short, typically. And so one idea is to combine it with other interventions like ibogaine or even lower doses of things like psilocybin to try to extend the plasticity window, because most of the things we're talking about actually increase plasticity, including electrical stimulation. But again, it's short-lived, stressful life events happen, that kind of reduces the effect. So you might be able to do lower doses of all of the above, and getting to Tim's point of sort of how do we do this ethically at scale. The best way to do that is follow a principle where you're doing the lowest dose possible to get the effect. And it's my intuition, actually, just combining them is probably the way to go. Plus, mindfulness and other things that you can do on top of it.
NIDA, the National Institute for Drug Abuse, is collaborating with us for using, because they were interested in a wearable TMS device. And there's some preliminary studies that I don't know the results yet, but that it was a lab, internal NIDA lab, that is pursuing this as a collaboration.
Thank you all.
And there is a link also with mind wandering and addiction, because people who are addicted often do it to suppress some thoughts, some rumination and depressive thoughts. So all the treatment, mindfulness, etc., where you accept your thoughts, can also have, positive effect on addiction.
So the conclusion is we should just combine all of this in one device. Then we can cure suffering.
Continue what you just mentioned now. If you look into ourselves, the neurons and all this is part of our hardware in some way. But there is software that's in some way that you ignore, all of you. Sorry. Software, I mean, today, most of what you've done, discuss about the neurons in the brain or part of the neuron, which is like the microtube, etc. But in addition to this, we've got software, the way we're thinking and all this. So if somebody even suffer from depression, sometimes it can be because, some experience that you've got, and sometimes if you teach him how to either to go beyond the ego, this is a part of the other way to teach suffering, or from the cognitive to change the way of thinking, to change the software that creates all this. The same with the anxiety, depression. And most of the people, I'm working with the National Health Service in England, and about 2 million people now refer to talking therapy. And all the talking therapies, they don't use any of this, just to talk with the patient, okay? You ignore it, okay? And many of them, there is a lot of way to improve the talking therapy today, okay? I don't think that it's perfect, far from being perfect. But I believe that if you combine what you're doing now with proper talking therapy, that can be even done not just with a psychologist, but you can, we computerize all the talking therapy and sometimes combine with this. And most of the people recover. So if you can combine this, because for example, if somebody suffers from depression, even if it's something physically, but we learn to overcome the depression using this, then sometimes you have to learn to start to have a relationship, to go back to work, etc. This is the neuron will not be enough. So if you combine all the aspects of this together with this, I believe we've got much better solution to reduce suffering. And I'd be happy to collaborate with any of you on this aspect. Thank you very much. And I want to thank you, all of you, because it was very, very interesting. Thank you.
Thank you. Yeah. May I comment on that? Yeah, so that's a very good point, and I just want to clarify something. I think all the technologies that we have been discussing here, including talking, they're all based on the premise of changing brain dynamics and then inducing plastic changes in the brain, that you change synapses and you rewire circuits. So all these techniques are actually doing something very similar, and the combination, it's very natural as well. Yeah.
And related to this, I like to say that, and it's probably I part this from Shenzhen too, flourishing is a verb, not a noun. It's not a state, but a process. So if we think of it that way, then, even to the point of can we just have technology that replaces the process of meditating to achieve, well-being? Yes, maybe, but maybe actually what that does is it frees us from the prison that we exist in, and then allows us to start on a new path. But that path is the technology isn't solving for that. It's making it possible for you to walk that path. And that path are things that, involve life practice, engagement with humans and with nature, and navigating that.
Yeah, and the power of, you can call it placebo or nocebo, or, in some African culture, there is the marabout or the sorcerer would say, you die tomorrow, and the person would die. This has been documented somewhere. And you can call it, power of nocebo, but the power of the mind on the body is incredible.
Totally agree. I'll just plug my talk tomorrow. We're talking about a project that Shenzhen's been working on called the Ramona Project, where we're leveraging LLMs and then coaches on top of that to provide some of the sort of context, the sort of support that you're talking about. And as far as I've seen in the literature, I think there's some work using TMS and cognitive behavior therapy, showing that the interaction between the two, you get that durability effect that I was talking about. So it doesn't make the TMS effect work any better, but over time, really you get it to work. And if you care about the human being at the end of the day, that's what you should be doing, right? So, totally agree. I think we are out of time. Thank you so much for staying late tonight.
Thank you.
This was very pleasurable.
Thank you.
Thank you all for staying.
Thank you.